Greetings and welcome to today's video. This will be a very special episode where I'll be going through a non-calculus proof for the volume of a sphere. This would not be possible without a particular mathematician, our favorite naked man who runs down the streets of Sicily. Yes, it's none other than Archimedes. In case you've never heard of Archimedes, this man was the stuff of myths and legends. One legendary quote attributed to him whilst establishing the law of the lever was that if anyone could give him a lever long enough and a place to stand, he could move the world. Another legend was that he designed a series of mirrors that could reflect and focus the heat of the sun into some kind of ship-burning death ray. This myth was sadly busted in the Mythbusters episode 46. But the story we are probably most familiar with was recorded by Vitruvius, an engineer who lived around 100 BC. He tells the story of General Hiero II of Syracuse, who suspected that he was being cheated by the goldsmith who made his crown. The general tasked Archimedes to determine if the crown was indeed made of solid gold. Archimedes, while bathing, discovers the principle of displacement, and he runs down the street naked shouting "Eureka!" or "I found it!" Basically, the idea is that if you take the crown and you immerse it in water, the water displaced would have the same volume as the crown. And you can use this idea to measure the volume of irregular solids. Other famous discoveries by Archimedes includes his principle, the Archimedes principle, that states that the upward buoyant force acting on an object is equal to the weight of the fluid that the body displaces. But his greatest discovery, so great that it was carved on his tombstone, was that the volume of a sphere is two-thirds that of a cylinder. Using the principle of displacement, Archimedes could measure the volume of spheres by dunking them in water. Then he could do the same, but this time with cylinders with the same radius and the same height 2 times the radius. He could then show that the volume of a sphere was two-thirds the volume of a cylinder, and this is independent of the radius chosen, and this was an amazing discovery in 200 BC. Since we know that the volume of a cylinder is base area times height, it would be pi r squared times 2r, so we can work out the volume of a sphere to be 4/3 pi r cubed. However, I would not call this a rigorous proof by any means, merely a really good observation. By the way, one last fact about this legendary man is that during the siege of Syracuse, the Romans invaded, and Archimedes was killed by a Roman soldier who told him to stop doing math, but he refused to stop. Students can learn from his deep passion for math. But for a more rigorous proof, we need to fast forward time about 1,700 years. We turn now to a 15th century mathematician by the name of Bonaventura Cavalieri, a contemporary and pen pal of Galileo. His work on the indivisibles led to Cavalieri's principle. Let me first explain this in 2 dimensions. Let's say we have an area bounded by 2 parallel lines, the easiest example being a triangle with the same base. His principle states that the areas must be the same if any parallel line that we draw between those 2 given parallel lines, as shown in orange. This parallel line intersects the 2 triangles to give us 2 equal segments, shown in red. We know this to be true for triangles of the common base and common height, and we can prove this using similarity. In summary, if they have the same length at any height, they must have the same area. In 3 dimensions, this principle tells us that for 2 volumes, say a right pyramid shown in green, and a blue oblique pyramid such that the apex is directly above one of the base vertices as shown in blue, these pyramids have the same base area and the same vertical height. The 3D version of Cavalieri's principle states that any horizontal plane that intersects these 2 pyramids, giving us equal areas, shown here in red, if they give us equal areas, then these two pyramids must have the same volume. And we can show that for two pyramids of the same height, these two red areas are equal using similarity. This will tell us also that the pyramid's volume is conserved under shearing. The intuition here is that by shifting these thinner and thinner slices of volumes parallel to the ground, the total volume doesn't change. Hence, if we can prove that the cross-sectional areas of two solids have the same area at all height, the two volumes must be equal. Now, before we apply Cavalieri's principle to find the volume of a sphere, we need to make this interesting observation that the volume of a cone with height 2 times the radius, that volume is 1/3 base area, which is pi r squared, times height 2r, which gives us 2/3 pi r cubed. And this volume, if we add it to the sphere's volume being 4/3 pi r cubed, it gives us the volume of a cylinder with base pi r squared and a height of 2r. So just nice, it gives us 2 pi r cubed. Now with this interesting observation, how can we apply Cavalieri's principle to prove the volume of a sphere? Well, first we need to make the sphere the subject. So volume of the sphere is going to be equals to the volume of a cylinder minus away the volume of a cone. But the trick is this, we don't use this cone. We're going to use two cones, each with a height of r instead. The volume will still be the same because each of these half-size cones are 1/3 pi r cubed. So add them together is still 2/3 pi r cubed. So the challenge that we have before us is to show that the cross-section of the sphere is equal to the cross-section of the hollowed-out cylinder at any height chosen. For simplicity, we're going to define the height h as the height above the center. Now, if we lob off a spherical cap from the sphere, we're going to get this red circle as the cross-sectional area. For the hollowed-out cylinder, once we lob off a bit of the top, we're going to get this weird red area. This is basically a circle minus away an inner circle. The proper name is an annulus, and that will be the cross-sectional area. So we need to show that these two red cross-sectional areas are equal. So at this point, I would like to encourage all the viewers to pause the video here and try to prove this for yourself. So for the sphere, the red area is a circle with radius big R. So the area is just simply pi big R squared. For the area of the annulus, it is the big circle minus away the small circle. So let's say that the big circle has a radius of r, which is also the radius of the sphere. So that area will be pi r squared. Minus away the area of the small circle, and let's call the radius a. So the area is going to be pi bracket small r squared minus away a squared. Now we're going to cut this cylinder in half vertically, and we're going to get this yellow right-angled triangle in the cross-section of the cone. And since the cone has a height of r and a base of r, the height of this yellow triangle will also be equal to a. So h equals to a. This tells us that the area formula can be simplified to pi r squared minus h squared. Next, let's look at this purple right-angled triangle in the vertical cross-section of the sphere. This right-angled triangle has a height of h, a base of r, and a hypotenuse that is small r, the radius of the sphere. So Pythagoras' theorem is going to tell us that this small r squared is equals to h squared plus big R squared. Using Pythagoras' theorem, we can simplify the equation that we have on the right-hand side, and that will give us pi big R squared equating the red cross-sectional areas of the sphere and the hollowed out cylinder. With that, we have finally shown that the volume of a sphere is equals to the volume of a cylinder minus the volume of these two cones. And that will give us 2 pi r cubed minus 2/3 pi r cubed to be equals to 4/3 pi r cubed. And that is the end of this video. If you have any questions, please post it in the comment section below. Don't forget to like and subscribe, and have a great day of learning.